Hello everybody. So in this video we're going to continue talking about chapter 14, which is Integral Calculus 1, specifically 14.3, which is about more methods of integration. So in the past section we looked at a very powerful method for integration that we know as integration by parts. However, integration by parts cannot be applied in all situations. Sometimes, even though you might apply it, it's not the most efficient method. So in this section, we're going to consider alternative methods of integration. Now, one of the important things here that you can see on the slide is a few trigonometric identities that can be very useful to solve certain integrals. So first of all, we have the Pythagorean identity of cosine squared plus sine squared equals 1. We can use this to solve certain integrals. Then 2 and 3 are interesting because some of you might not have seen them before, but these are just derived from the double angle identity for cosine. So we have one, in the end we get an identity for sine squared, another one for cosine squared. And then finally we have this other one, which is in terms of secant squared and tangent squared, which is obviously derived from the Pythagorean identity. Very well, so here we are in example 14.13, where they ask us to evaluate a couple of integrals. So the first one says integral of sine squared of x dx. So from the previous identity number 2, we can rewrite this as the integral of 1 minus cosine of 2x and this over 2 dx. And this is much easier to integrate because we know that we can rewrite this simply as 1/2 times the integral of 1 minus cosine of 2x dx. Some people prefer to use a parenthesis here. It's okay if you don't though. So this is easy to integrate because we already know what this will be from the previous examples. We know that this is going to equal 1/2 times x, which is the integral of 1, and then minus 1/2 times sine of 2x. And obviously, we can't forget plus c. For b, they ask us to integrate cosine to the 4th power of theta. So here we can also use one of the previous identities, specifically the third one. And notice that we can rewrite this as being equal to the integral of 1 plus cosine of 2 theta over 2 and this squared. Okay, and let's not forget this. So then we can expand this, and this is going to give us 1/4 integral. Now remember that this is the same as going this squared and this squared, right? It would be the same thing. So that's what we're doing here. So this becomes 4, so I take it out as a constant. It will be 1/4. And now I have to expand the top part, and the expansion of that is going to give us 1 plus 2 times cosine of 2 theta, and this plus cosine squared of 2 theta. Okay, and then we can rewrite this as being equal to, notice that we're going to have to substitute here again, right? So continuing, we would say that this is equal to 1/4 the integral of 1 plus 2 times cosine of 2 theta. And then we said that we would have to apply the identity to this part, right? The previous identity, number 3. We would have to apply it to this part as well. And from there, we're going to get that this is equal to plus 1 plus cosine of 4 theta. So be careful because here it's going to be 4 theta, not 2 theta. Why is that? Because the identity that we had was 4 theta itself, but in this case we have 2 theta, so it'll be now 4 theta. So 1 plus 4 theta, and this over 2. And then don't forget the parenthesis and derivative of theta. Okay, and then from here, notice that we can get this 2 here as a common denominator for the whole expression and take it out and multiply the 1/4 as 1/2. So this would be then equal to 1/8 times the integral of 2 plus 4 cosine of 2 theta. I'm running out of space again, but I'll just move up here to the right. So 2 plus 4 cosine of 2 theta, and this just plus 1 plus cosine of 4 theta. And let's not forget this. But then this is easy just to integrate now as it is. And then this, we're going to get that this is equal to 1/8 times 2 theta plus, so sine of 2 theta plus theta, which is the integral of 1, plus, and here we can write 1/4 sine of 4 theta. And let's not forget plus c. So next we have example 14.14, and they ask us to evaluate the integral of secant of x dx. Now in some textbooks, this is one of the commonly known integrals, and it is actually equal to the natural logarithm of tangent of x, of the absolute value of tangent of x plus secant of x, and this plus c. But what happens in the case where they say, well, prove that this is true? How do we do this? Well, there's a little trick that you can do with this, and you will see in a minute why. So we would say, okay, let's say that the integral of secant of x dx is equal to multiplying this by an expression. And this expression that we multiplied is a fraction. So it would be tangent of x plus secant of x, of course, over the same thing, right? So tangent of x plus secant of x, and don't forget dx. So now we can multiply by secant, and we're going to get the expression we want. So then this is going to equal the integral of secant of x times tangent of x, and we know that this is the derivative of secant, plus secant squared of x, which by the way is the derivative of tangent, and this over tangent of x plus secant of x, and dx. So at this point, now we can do a u substitution. Because if we say, well, let's make u equal to tangent of x plus secant of x, then the derivative of this is going to be the derivative of tangent, which we know is secant times tangent. So it would be secant of x times tangent of x plus secant squared of x dx. So notice that this is the same expression we have up here. And this would be what we substitute for u. So we can simply rewrite this as equal to the integral of 1 over u du. And then we're going to get the expression that we have up here. Because if we solve for this, this is simply going to be natural logarithm of the absolute value of u plus c, which if we substitute back in, it's going to be natural logarithm of the absolute value of tangent of x plus secant of x plus c. Very well, so next in the video is example 14.15, and they want us to evaluate this time secant cubed of x dx. So what can we do here? Well, notice that this we can rewrite. We can say that this is the same as saying integral of secant of x times secant squared of x dx. And the reason we do that is that we know that this is the derivative of tangent. So we can say that this part here is u, and we can say that this is the derivative of v, and do integration by parts. So we would say, okay, let's make u equal to secant of x. Therefore, derivative of u is going to be secant of x times tangent of x. And if we say derivative of v is secant squared of x dx, that means that v is going to be tan of x. And then we can just do integration by parts. So we could rewrite the integral of secant cubed of x dx, and we can say it's the same as u times v, which would then be secant of x times tangent of x, minus the integral of v du, right? So, but notice that v is tangent of x and du is secant times tangent. So we know that this is the same as saying secant of x times tangent squared of x dx. Okay, so then we end up with another integral here that we will have to redo. So how do we do this? Well, notice that I can rewrite tangent in terms of secant, right? So I can say that this is the same as minus secant times secant squared minus 1. And then notice that we can separate this into two different integrals, which would then be, let's just rewrite the whole thing. So this would be equal to secant of x tangent of x minus secant cubed of x plus the integral of secant of x. And we can't forget dx. Okay, so then it seems like we're stuck here, but no, right? We're not. Why? Well, because notice that this here, this expression here is the same as the one we had in the beginning. And then once you get into that, once you repeat the cycle or you get the same answer that you had before, you can just use this to solve the problem. So we could rewrite this as 2 times the integral of secant cubed of x dx is going to equal secant of x times tangent of x minus the integral of secant of x dx. But we already learned that this is equal to the, this is a plus, not a minus, because this is gone. So plus the integral of this, which we already know, is natural logarithm of the absolute value of secant of x plus tangent of x. And then we say plus c. So finally, all we have to do really is just divide everything by 2. Divide both sides by 2. So here we're going to get this over 2. Remember that dividing by 2 should not affect this letter c, which represents any constant. So dividing or multiplying by 2 should not affect. So once we get to this point, we have found the solution. Okay, so here we are in example 14.6, which is going to be the last one on this video. And they ask us to evaluate the integral of sine cubed of x times cosine cubed of x dx. So remember that sine and cosine are basically the derivatives of each other. Well, specifically cosine is the derivative of sine and negative sine is the derivative of cosine. So basically it's very obvious that we can do u substitution in this case. How so? Well, notice that we can rewrite this. We can say that this is equal to the integral of sine cubed of x times cosine squared of x times cosine of x dx. So I'm going to use this as the derivative part. And I'm going to do u substitution. But first, I need to convert this into terms of sine. Leave this in terms of sine and not in terms of cosine. But we know from the Pythagorean identity that cosine squared is simply 1 minus sine squared. So we can say that this is equal to the integral of sine cubed of x times 1 minus sine squared of x times cosine of x dx. And then we can just say that this is simply going to be equal to the integral of sine cubed minus sine to the 5, right? So sine to the 5 of x and cosine of x dx. So now we can do a simple u substitution, because then we can say, well, let's make u simply equal to sine of x, and derivative of u is going to equal cosine of x dx. So we have everything we need to substitute. Eventually, when you guys get really good at this, you're not even going to need to do the u substitution. You will just know how to proceed and basically do the u substitution in your mind. But for now, we're going to do everything step by step. Okay, so this is going to be equal to the same as saying the integral of u cubed minus u to the 5 du. And then this would simply be u to the 4 over 4 minus u to the 6 over 6 plus c. And then finally, we just plug in back for sine, and we get the final answer, which is going to be sine to the 4 of x over 4 minus sine to the 6 of x over 6 plus c.